Hello. Let's talk rational exponents. So as we can see here, we have a power, and that power has an exponent. And as we can see, it is rational. In other words, it is a fraction. It has a numerator and a denominator. So the cool thing about this is we can actually rewrite it in a different form, where the denominator becomes the root and the numerator becomes the power. So the interesting thing about this is that the power can also go on the outside. So right now this is kind of abstract, right? We're kind of dealing with some variables here, but we can put in numbers. So for example, if we had 4 to the 1/2, we can really think about this as 4 to the second root, and we're going to raise that to the first power. So again, kind of convoluted, but if we kind of think about this, this is really the square root of 4. And normally when we do the square root, we don't write the root in front, we just kind of assume it. So this can kind of go poof as well. And then we know the square root of 4 is 2. So let's kind of get some extra examples to kind of get a better idea of these topics right here. So let's take a look at 5 to the 3/4. Again, the denominator becomes the root. So this is a 4th root of 5 to the 3rd power. 6 to the 1/5, well, again, 5 is the root, 6 is under the square root, and then it's raised to the 1st power. Let's do these other ones. So then this is a square root of 2. We're going to raise it to the 3rd power. And then same thing for 10. This is a cube root, and we're raising it to the 5th power. Notice again how sometimes I put the exponent on the inside and sometimes I put the exponent on the outside. It does not matter. All right, let's kind of work backwards here. So again, here is our root. It's a cube root, so that becomes the denominator of this power. And then since we're raising it to the 5th power, that becomes my numerator. So this is 4 to the 5/3. The root is 4, so the denominator is also 4, and the numerator is 8. What do you notice about this, though? Well, taking a look at my exponents, oh my goodness, 8/4, I can reduce that. That's 3 squared. And we can evaluate that to be 9. Let's deal with 5 to the 4th, or the square root of 5 to the 4th. I actually kind of missed this because, oh my gosh, there's no root. But when there is no root, there's a secret root of 2 because it is a square root. So rewriting this in a different form, we get 5 to the 4/2. And then we can again simplify that fraction, and it turns out to be 5 squared, which we can evaluate to be 25. Let's take a look at, or you know what, actually I want to take a second just to kind of show some calculator skills here. So I'm going to pull up a calculator. You can pull up a graphing calculator or a scientific calculator. Either will work. And if we do the square root of 5 to the 4th power, let's see what we get. Oh, 25. My answer is right. So you can always check your work with a calculator, which is why I kind of like rational exponents. You're just evaluating. And let's go on to D. So let's convert this to a different form. This becomes my denominator. And the 7 becomes my numerator. 10 to the 7/5. So hopefully you're feeling a little bit more comfortable with this. And now let's do some evaluating. So here, we couldn't really do anything, but sometimes we can. So let's take a look at this. -8, and we have to take the cube root of that and then square it. So when I'm taking a cube root, I'm asking myself, what number times itself 3 times is -8? And the answer to that question turns out to be -2. And it's okay that it's a negative because it is an odd power. So we have -2 squared. And then since 2 is an even power, when I multiply -2 by itself, I get positive 4. So here's the key idea I want you to take away with. You could square this -8 and then cube root it, but I think it's much easier to always make things smaller before you make them bigger. So deal with the root first. Then raise to the other power. So let's try another example. So as you can see for number 5, now there's two things. It's a binomial, but we can kind of just deal with these individually and then put them together at the end. So I see 100 to the 1/2 power. I'm going to rewrite that as a square root. Again, do you need this root and do you need this exponent right here? No, but I'm just going to be putting them there just for the sake of like getting in the habit of converting between the two forms. So 27, this is a cube root because the denominator is 3, and I'm again raising it to the first power. At this point, I can do the square root of 100 in my head, right? What number times itself is 100? That's just 10. The cube root of 27, what number times itself 3 times is 27? Well, that is going to be 3, because 3 times 3 is 9, and then times the number 3 is 27. And lastly, we can put these together, and 10 minus 3 is 7. Let's take a look at 4 to the 5/2. I'm going to do this converting for us first. So this becomes our root. I'm taking a square root of 4, and I'm going to raise it to the 5th power. So again, I'm going to deal with this root before I deal with the power, just to make things easier, right? So the numbers don't get too big. The square root of 4 is 2, and I'm going to raise that to the 5th power, which is 5. And 2 to the 5th, I'm going to go over to my power sheet. 2 to the 5th power is 32. All right. Let's take a look here. Interesting thing is that there's a negative. Do you think that this is going to just be -9 to the 3/2? It is actually not going to be that, because when we have a negative exponent, all that's telling me to do is to take a reciprocal. So really, this brings it down to the denominator, and then we can evaluate. So again, since the denominator is still 2, that's going to be a square root. So the square root of 9, again, you don't have to put that root there, and I'm going to raise it to the 3rd power. So what do I want to do first? Square root the 9 or raise it to the 3rd power? I think I'm going to deal with the square root of 9, since I know it's just going to be 3. And then 3 to the 3rd power is 27. So your final answer is 1/27. All right, let's kind of review some exponent properties here. So we've seen these before, but I'm just going to kind of quickly run through them as a quick refresher. So when you have two powers with the same base, you add their exponents. When you have a power to a power, that's when you are going to multiply. The way I kind of remember the difference between these two, because people often mix them up, is that when they are on the same level, that's when you add. And then when you have kind of things on different levels, that's when you multiply. Let's talk about here. So when we have a product raised to a power, you can kind of think about distributing that power. When you have a negative exponent, we just kind of talked about this, we are going to move it across the fraction bar and lose the negative exponent. When we have a quotient, or in other words, we are dividing powers with the same base, we are going to subtract their exponents. Kind of similar to this rule right here, when we have an entire quotient raised to a power, we can again just kind of think about as distributing that power to both of them. And by that same logic, it also works for square roots. So again, kind of all of these are equivalent. So if you're able just to remember that, oh, when it's all one term, you can just kind of break it apart. That's how I think about it. So let's take a look here. Do I add or multiply? So I would say add, since they have the same base. So I get 5 to the 1/2 plus 3/2. Just kind of a quick refresher for some exponents right here. I see that they have the same base, so I'm going to just add across for their numerators. So I get 4, and the denominators remain the same as a half. So 5 to the 4/2. I can reduce that fraction up in an exponent, and I get 5 squared. Lastly, 5 squared, I know that is 25. Let's take a look here. So here, am I going to multiply or am I going to add? I'm going to multiply here. So I have 3 to the 5/2 times 2. The reason why I left this little gap right here is because what's the denominator in that 2? Well, it's just a 1. And then when I'm multiplying fractions, I don't need a common denominator. I just multiply across. So I get 3 to the 10 over 2. Lastly, just like before, we're going to reduce this fraction right here. 10 divided by 2 is 5. So this is 3 to the 5th. And lastly, using my power chart, I go to 3 and I raise it to the 5th power. So that is 243. Let's keep it rolling. Here, we got two options. Either we can do this multiplication first, or we can kind of distribute this power right here since it is all one term, right? If this was a plus, then we could not do it. But since it's multiplying, I can kind of think about them as separate terms. So that I'm actually going to do this. And the reason why is because when I raise 16 to the 1/2 and the 9 to the 1/2, well, I know when I raise something to the half, that's really a square root. And look at this. 16 and 9 are both perfect squares. So the square root of 16 is 4, and the square root of 9 is 3. 4 times 3 is 12, and that is my final answer. Let's take a look at 10. So 10, there's kind of some different things going on. I see this larger square root, not a square root, a cube root here. And then I see some stuff on the inside. So just like how we did when we were simplifying exponent rules, kind of make things as simplest as possible on the inside before dealing with those outside things. So I still have a cube root. I'm going to leave that alone for now. 24 divided by 3 simplifies to 8. And there's still that x to the 6th there. Yes, I could deal with this cube root of 8 because I know that is 2, but then I'm going to have to deal with this variable as well. So I think here it would be beneficial to switch to a different form. So it's still 8x to the 6th, but I have to raise that whole thing to the 1/3 power. And the reason why it's a third is because the denominator comes from the root, and then the power on this whole quantity on the inside is just 1. So hence, this becomes 8x to the 6th to the 1/3. So then we have 8 to the 1/3 and x to the 6th times 1/3. I multiply the exponents since I have a power to a power. 8 to the 1/3 is the cube root of 8, which is 2. And then x to the 6th times 1/3. I multiply across and I get x to the 6/3, which reduces to x squared. And that is my final answer. Let's take a look here. So again, we're just kind of using different exponent properties here, but now we're just kind of throwing some fraction operations in there. Automatically, I see that they have the same denominator, so I figure this is probably going to work out. I also notice that I'm dividing things with the same base. So I know I can actually subtract their exponents. So this is 4 to the 5/2 minus 1/2. Putting these together, 5/2 minus 1/2, I just add across. So that's going to be 4, and the denominator stays the same. when you add or subtract fractions. 4/2, I know I can reduce that, so this is 4 squared, and that is equal to 16. All right, let's go on to 12, kind of wrap this up. I see 27 to the 1/3 and the 64 to the 1/3 right off the bat, but I'm looking to see if I can reduce this fraction first. So I know 64 is like 8 squared. I know 27 is like 3 to the 3rd. So they don't share any common factors, right? There's nothing I can simplify out of this fraction. So my gut instinct is probably just to distribute this 1/3. But notice how I checked to see if it was reducible at first. So this is 27 to the 1/3 over 64 to the 1/3. And then 1/3 really just means a cube root. So this is the cube root of 27 over the cube root of 64. Again, it's to the first power, but do you need that? No. The cube root of 27 is 3, and the cube root of 64 is 4. Lastly, my answer is 3/4, and I can't reduce that, so my job is done. 2 more, and then we're going to kind of do some problems on your own, and we're going to put those problems up on the whiteboard. But let's take a look here. What do I want to do? I see 2 quantities that I can probably put together, but I can't do it right off the bat because this one has an exponent that I have to deal with first. And exponents come before multiplying when you're thinking about PEMDAS. Right? Exponents come before multiplying. So let's deal with that right here. I have a power to a power, so I'm going to multiply. Again, this is really 2 over 1, and I can just multiply those fractions across. So I get A to the 8/3 and B to the 2/2. 2 things. 1, I can simplify this fraction. And 2, I can put these 2 together since they have the same base. Can I combine these 2? No, because they have different bases. So let's take a look at these A's. Since they have a common denominator, I can just add. So this is 9/3, the denominator stays the same, and this is B to the 1st. Lastly, I can reduce this fraction, and I get my final answer to be A to the 3rd, B to the 1st. But you don't need that first power, so you can also just leave it like this. Last one, number 14. So I see this is this is to the 4th root. I know the power is 1. So this is really x to the 4th, y to the 8th, z to the 12th, all raised to the 1/4 power. There was nothing I could combine in here, so that's why I chose to convert. And then I am multiplying these exponents. 1/4 of 4 is 1. 1/4 of 8 is 2. 1/4 of 12 is 3. And my job's done. Do I need these parentheses right here? No, not really. I don't have to distribute anything, so I'm kind of just good like this. All right. Thank you for listening, and let's try some problems on our own now.